Hey folks, so we're going to go ahead and take a look at what now happens with electric field lines, which are going to permeate from materials and objects that have electrical charges. So what we see here on this diagram to the left, we see what is a representation and a model of what the electric field lines actually look like and actually behave as. The big point here is we always reference this as what a positive charge would do, which feels backwards based on the knowledge that the negative charges, the electrons, are going to be the ones that are actually doing the moving. So we take this positive charge, we place a positive test charge in the vicinity here, and we see which direction it would move. So by taking a positive charge and using a positive test particle, what is observed is that test particle moves away from that positive charge. Thus, the field lines are drawn with how a positive charge will respond within an electric field. If we flip the script on this and we have a negative charge, the negative charge is simply going to be the inverse of this, right? We're going to actually see that positive charge move in towards the negative as opposed to moving away from the positive. And this field really comes back to the idea of what a force actually is, where there are contact forces and there are field forces. And recall the field forces that exist are the gravitational fields, magnetic fields, and electric fields. So that's what's happening here, right? We get these fields that are created based on the material having charge, and that charge is what is going to exert the force on the different materials. For example, by having these lines permeate outward, we're going to see how far their presence is actually going to be influential on a material. As we've previously seen with Coulomb's law, that electrical force falls off as the distance squared, right? It's an inverse square law. So what we would expect to see is that the further away we get, the weaker that electrical force becomes. One way that you can consider this is if we start drawing concentric circles around the point charge. So if we do a circle right here, we can look at the density of the field lines and compare it to a circle right here. And we can draw another circle even further out, right, to just try to encompass everything that we have here. And now look at the density of these field lines. If we look at the interior circle, right, the smallest one, the closest one, notice how close and compact these field lines are. As you get further away, look at how much space now exists between these field lines, right? That sector gets bigger the further away we get. And the farthest one away on this diagram, we see that our sectors are even further away, which indicates a weakening of the electric field as you get further and further away. That's how we can see this here. Higher density is going to represent a stronger field. Lower density is going to represent a lower field. And we can get that density either based on the number of lines themselves or based on how close the lines happen to be. If we took a particle, and let's say we took a particle right here, let's call it a negative charge, and we had the field lines do something like this, right, where we had many, many, many field lines coming in. This would have a higher relative charge and a stronger electric field in general than the positive charge drawn here, simply because we have more field lines present. So as we get further away, the density of those lines is going to be greater than the density of the lines on the diagram to the left. So as we look here, right, the direction of these field lines is going to be indicated via the arrows. Again, the direction that a positive charge would move if it was in the vicinity. So on the top left, where we have our positive charge, we're going to see a positive test charge flow away, thus the arrows point away from that charge. Here we see a negative charge, and that positive would then go towards that negatively charged area, right? It's going to flow inward. As a result of this, we see the positive charge going out, the negative charge going in, where we get the diagram in the bottom left, which is how these field lines intersect and connect, we can actually draw a dotted line between each one of these field lines, and there we can see that connection, right? That's where they're going to be drawn together, and we can even include the arrowheads in there to show which direction they're going to go. That is going to be the attraction that's going to draw these materials together. Now, if we look at the positive and positive in the bottom right-hand corner, notice how these field lines are still permeating outward, but once they make contact, because they're going opposite directions, they're going to push off of each other, and instead of connecting to draw together, we're actually going to see them push off of each other in repulsion. So these field lines are the reason why we get repulsion and why we get attraction. It's based on how they intersect with one another, how they combine or refuse to combine to get that pushing away or pulling together that we see with the electric fields. Now, as we look at this example here on FET, right? We've used these FET simulations a fair amount. We've got our charges in the bottom. We have our sensor here that we can use, and then we have just a few options, right? So I'm going to go ahead and turn on the grid just to put that on, and I'm going to put a single positive charge out here. Now, the way that this simulation is going to show strength, it's going to be how clear and how bright the white arrows are. And as we see, as we get further away, we notice that the arrows get dimmer and dimmer and dimmer and dimmer. If we add another charge in here, right on top of it, notice how that field gets brighter further away, right? So we get brighter and brighter and brighter, and that is going to act to increase the relative strength of that particular point, right? So I can take some of these away, and we can go back to that initial single point charge. Notice again, pointing away, if I do a single positive charge further out, I've added more charge to the system, so we're going to see the overall web page here get brighter because there's more general charge, so we're going to have more electric strength, more electrical fields to work with. But notice again, we're pointing away, but now look at how these field lines start to intersect with each other and interact and push away, right? There is no connection, so at this point, this simulation is showing just a straight vertical line. If I replace the positive charge with a negative charge, now notice how these field lines intersect with one another, right? They physically connect, they go away from the positive, they go towards the negative, and we're a nice bright area here, and we see this charge strength fall off as that distance increases. If we add another charge here, it gets stronger. Add another charge, even more so. And you can see how these positives are then actually bending towards the negative. So if we get rid of it and then bring it back, you can see the positive bend more strongly towards that negative. If we add more positive, right, it's just going to act to balance things out a little bit. But we can see that attraction right there. If I start moving the location of these charges, all right, we can get different field line appearances, right? Because now we have 5 charges in the area as opposed to just the 1 or 2. So we can start developing odd patterns where we still see attraction, we still see repulsion, but at the end of the day, it's how these charges are going to interact with one another to get the fields that we see. The sensor here at the bottom, if I bring this in, right now, depending on where this moves, this is going to tell us the relative strength. So we're going to bring this down to just our positive charge again. And as we go to just that singular charge, notice how as we get closer, the arrow gets exponentially longer the closer we get to that charge. As we get further away, it gets exponentially shorter. We make this point stronger. We add more charge to it. In that same location, we're seeing an increase in that sensor length, indicating the amount of force that's present there. Exponentially longer, exponentially shorter as we get further and further away. So again, this video here, looking at those electric field lines, how they interact with one another, how they cause the attraction and the repulsion that we see, and then giving you just a nice visual demonstration of these electric field lines. Thanks, guys.